Gauss law. Everybody learn in college physics Gauss law. The equation is given, and usually they go to the exercise of calculating capacitor and stuff. But here, let's give a moment to understand the profound meaning of this Gauss law, what it is basically. The Gauss law states that the electric field is a function of charge. Charge defined electric field. But electric field is the function of potential. So if you take divergent, gradient, okay, so it's a second order derivatives. Okay, that's what this means, and this is called Poisson's equation. So this is a differential equation. What it is if we solve the differential equation, we know what the field look like, electric field look like for the given distribution of charge. Now the electric charge moves, then suddenly phi function change. If phi is given, then we can figure out how the electric charge is distributed in the space. So basically that's what it is. So defining moment is here. The Gauss claimed this, and that seemed to be consistent with experimental result. Okay, and Maxwell's equation include this Gauss law. Okay, for the static, electric and magnetic field. That's the equation. There's no time t in the equation. That means stationary, static. Okay, and when time comes in, then things start changing around, which become two other Maxwell's equation. Okay, so basically potential field phi and charge in the space are related, and this relation is given by the Gauss law equation. Now when you take a volume integral of divergent E, the math formula tell us that it's same as taking surface integral on E, but the other side has a law. So what's happened is volume integral of this become total charge Q. So total charge Q is given by this surface integral. So what it means is you have some charge inside total Q, and you take a surface integral and electric field going out. So you collect all the information about how much electric field going out from this area. We can figure out the total charge. So this is the integral form of the equation. It's basically same as differential equation. It just integral form is easier to use because you don't have to solve differential equation. Now example is, I hope you did this already. The electric field is potential V divided by distance L, and divergent E is this charge. Now the sign is depend on which sign you take, which this is the enclosure of the surface integral. Okay, and we ignore this fringe effect. Everything is straight down. Okay, so B equal LE, then from this equation capacitor is defined as the CV equal Q. Then we can calculate the capacitance of this configuration. Okay, so we can calculate the capacitance using the Gauss integral formula. Instead of taking integral, we just multiply the area because we assume everything is going straight down. So that's easy integration. Is solving Poisson's equation using symmetric property. So the Gauss law is not necessary to solve Poisson's equation. For example, in this case, you have a conductor, mirror, and the charge is sitting in front. So how do you calculate the field? The charge is here, and field, how the field, electric field look like in front of the conductor. Okay, so the Q is a charge. We set the mirror charge. This is artificial to solve the this differential equation. This equation, okay? Then what kind of function is going to satisfy this? We know it because it's a Q 4 pi. This is the equation. Okay, is there any other function that satisfies this Poisson's equation? Actually no, except for constant, because when you take integral, then there will be a constant. So potential is always subject to the constant, depend on the reference point in the potential change. Now, having this mirror image, we can come up with this equation, and this satisfies the condition that R equal R prime, the potential is 0, because from here to here, this is center point, the potential 0. Then sigma d is, you take a distance d and check. This is a volume, rho is a volume charge distribution, but sigma is a surface charge distribution. How the charge is distributed on the mirror, we can get that by taking derivative of phi, and that's the way how it's look like. So if you put one charge in front of mirror, say we look at the mirror in the front, you put the charge in front, then electric charge is going to be distributed like that, and probably it's going to be like distribution like this. So if this is the positive, then negative is gonna distribute, means the negative is pulled to the surface area. Okay, so this is a way to solve Poisson's equation without the electrical field using Gauss formula. The Gauss formula is also applied to the potential rho m magnetic field. Okay, magnetic field, the Poisson's equation, when there is the magnetization m exists, it's become like this. You can look at the reference book or textbook. Okay, so using this, potential field of magnetic field become like very similar to what we had in the mirror, but its difference is here, ds. Okay, so what happened is m is going this way. There's no true magnetic charge, it's all caused by the dipolar. So the h is going backward and also go around. So what happened is h is against m, so magnetized materials always subject to demagnetization, because h is going backward within against m direction. So eventually magnetized material become demagnetized. Okay, the B flux is the addition of this, and this is consistent, go from North Pole to South Pole, consistently flow, make a circle. So there's no true charge in the magnetic world. That's why this is zero all the time. Okay, so for magnetic field, divergent B is zero. Okay, so that's what the Gauss law is about. So we have other videos prepared, and please check out. I hope you enjoyed listening to these videos and learn something new. Thank you for listening.